Hello there, welcome to this video. This is for Solifillo and it's summer 17, question paper 42. Suggest the mechanism for the reaction of 2-chlorobutane with iodide ions. Draw out these steps involved, including those things there. All right, now this looks like in isolation, doesn't it? But it's part of a rates question, and if you did it properly, you would have figured out that the chlorobutane from the previous part of the question, the chlorobutane and the iodide ions are in the rate equation. Okay. Now, because they're in the rate equation, so therefore the rate is going to equal the chlorobutane, and the iodide ions. Because of this, it's going to be a bimolecular mechanism because there's two things in the rate equation, in the rate determining step, and therefore it's going to be an SN2 mechanism. Okay, so believe it or not, if you got an SN2 mechanism, if you got this as your rate equation for the previous step, then you should realize it's SN2 because obviously there's two species involved in the rate determining step. If you only got one thing, if you did it wrong the previous bit, and you only got one thing, well then you've got to draw an SN1 mechanism. Okay, so believe it or not, you can either pick an SN2 mechanism for this or an SN1 mechanism, but it depends on your previous answer whether you get all the marks right. But the correct answer is an SN2 mechanism, so that's what I'm going to do. All right, so let's first of all draw chlorobutane. So 1, 2, 3, 4, and there's a chlorine on number 2. And as you can see, it's a secondary halogen alkane. And immediately that should tell you, since it's a secondary halogen alkane, it will go for an SN2. Okay, only tertiaries, secondaries go for SN2, tertiaries go for SN3. All right, so there you go. But it wants structure to this. So I'm going to redraw this guy here. Okay, so I'm going to draw it like this. I'm going to draw the thing I want to get rid of like that, and then I'm going to draw three things coming from this carbon like this. One of them is going to be a hydrogen, the other is going to be a CH3, and the other is going to be a C2H5. Okay, so that's how I'm going to approach this. Let's get rid of that and that. So there's my 2-chlorobutane. Let me get rid of all of this. Got a question, just ask. Okay, all right. So the iodide ion is going to approach from here. There's my iodide ion, and you've got to show it's got a lone pair. And these electrons, let's try and give it some color. These electrons are going to attack this. Why? Why is it going to attack this? Well, because, as you all know, this is delta minus and this is delta plus. So we've got to do lone pairs, done there, and dipoles. All right, there's a lone pair on the left. There you go. So that's the first part of the mechanism. As this approaches, this is going to slowly try and leave. Okay, so we get our intermediate. Now the intermediate is we're going to get the iodine. Let's pick another color. Let's pick green. The iodine is going to be on one side. It's going to be a partial bond. And the CO is going to leave. But the other things are going to be in the same plane. So the hydrogen, the CH3, and the C2H5 is going to be like this. Now, what shape is this? Well, these are in the same plane. So this is actually a pyramidal. What's it called? Pyramidal? Bipyramidal. This is trigonal bipyramidal. When you've got something, you've got a triangle and something at the bottom. There's the iodine at the top, the chlorine's leaving, and you've got an H, it's my carbon, you've got a CH3 and a C2H5. Okay, so that's what this is, even though I'm drawing it pretty badly there. But this is what happens. So as that goes in, what happens then? Well, as this moves in, this leaves, obviously. And the thing, if you remember, flips over. So you have I, you have C, H. You've got the, what's going on? CH3 and the C2H5. Okay, so that's the mechanism. Plus, you've got to balance the thing. So plus Cl minus there. Okay, so that's what happens there. This whole thing is going to have a negative charge because the thing adding has a negative charge. Okay, I hope that makes sense. If you don't understand that, please give me a shout. But that's this is an SN2 mechanism. Now, NS, this part is obviously nucleophilic substitution. Okay, and this 2 means bimolecular. And that's because in the rate equation, you get the 2 terms. All right, so that's an SN2 mechanism. There you go. Now, the reaction was carried out using a single isomer of 2-chlorobutane. Now, as you can see, this thing shows optical properties. Using your mechanism to predict whether the product will be a single optical isomer or a mixture. Well, what happens is the stereochemistry or the stereochemistry, it flips. Okay, so what happens is you start off, let me try and draw what I mean. You start off with, let me draw it nicer. You start off with this. Oops, that's not very nice at all. You start off with this kind of shape with the chlorine there, and this bit flips over and you end up with the iodine and like that. So no, you don't get a pair. You get the flip over. You do get one optical isomer. So if it's SN2, you only get one optical isomer. Okay. Now I think it's worth doing the SN1 mechanism, even though it's not the absolute correct answer, but let's do that anyway. All right, and let's pretend you got an SN1 as the answer. So let's start again. Let's use a red pen. So chlorine there, everything's the same. This is C2H5, and this is CH3. Okay, the first thing that happens if it's an SN1, this leaves, and then you end up with this guy. CH3 and C2H5. Now this is plus. There you go. And then what happens then is the iodine comes on with its lone pair, and it attacks either from the top or from the bottom, because this is a planar thing. So you either get this thing with the iodine at the top or this thing with the iodine at the bottom. So if it was an SN1 mechanism, you'd end up with 2 optical isomers. Okay, it's a nice question, this actually. So I hope that makes sense. Solofellow has asked for another one, so let me stop this now and do her other question. Okay, so this is the second one she's asking about. Now, I didn't read the previous bit, but let's assume it's a kind of similar thing. All right, so we've got to do the mechanism for the reaction of 1-chloro-1-phenylethane with hydroxide ion. So let's draw it. Right, it's based on obviously an ethane molecule, and there's a chlorine on 1. Oh, ethane, what am I doing? Let's start again. Sorry about that. All right, it's based on an ethane molecule, isn't it? It's an ethane molecule, and it's got 1-chloro. And what's the other one? 1-phenyl. There's a phenyl as well. And there you go. All right. Now, that's these are 2 big bulky groups. Okay. Well, it's not that bulky, is it? The methyl. All right. But let's assume, and I don't know the answer to the first bit, but again, it's a rates question. I'm assuming anyway. It's a rates question. And if you got the answer, the rate equals K into the phenyl thing and the hydroxide thing, if you got that, well, it's going to be an SN2 because there's 2 things in the rate equation. But if you got in the previous part just that bit, it's going to be an SN1. Okay. Now, I honestly don't know what the previous question was, so I'm going to assume it's an SN1. So I'm going to assume you got. Oh, sorry, this is 1. So I'm going to assume you got this for the previous part. If you didn't, give me a shout. Maybe I can change this for tomorrow. But I don't know what the question is. So I've got other things to do. I'm afraid I'm a bit rushed today. All right, so let's do an SN1 for this one. Let's assume it's an SN1. So I'm going to draw the major bit, which is the CCl. And I'm going to draw my 3-dimensional thing like that. One of the things is a CH3. Another of the things is a phenyl group. And the other one is an H. So this is, I'm going to do an SN1 mechanism. First of all, delta minus, delta plus. I've got to put my dipoles in. Lone pairs, what attacks hydroxide ion? So let me put my hydroxide ion here. There it is. It's the oxygen of the hydroxide ion that's going to attack. and that is going to attack that, and at the same time that's going to leave. Oh, sorry, I've done an SN2, haven't I? Anyway, let me do SN2 for now then. So dot 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 C dot 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 CL, and then these things are in a plane. Oh, that's awful, isn't it? CH3 H. These are in a plane. This is above the plane and below the plane. As I did in the previous bit, it looks like this, something like that. All right, and then the electron's going to leave here, and I'm going to get that, my benzene bit, my hydrogen, I guess, and then my CH3. Okay, so if this is, even though I've been saying SN1 all the time, I've just done the SN2. So I've done this, haven't I? Assuming that this and this are in the rate determining steps. All right, so there you go. So if I started off with one optical isomer here, single optical isomer, I only get one optical isomer here. All right, so the answer here would be 1. And why? Well, because the thing flips over, but it attacks from this direction only. The thing flips over, so you only get one product, one optical isomer. So let me do the same thing now, assuming SM1, which I meant to do in the first place. All right, so let's get rid of all this rubbish and start again, and we'll do SM1. So Oliver, if I'm making a mess of this, give me a shout, and I'll try and do one tomorrow. Okay, so let's start again. CCl. 1, 2, 3. One of them is a benzene ring. One of them is a hydrogen. One of them is CH3. There you go. So if it's SM1, this has delta plus, delta minus. This leaves first, and this leaves us with this weird thing. Okay, H, CH3, and my phenyl bits. Okay, now this is plus, and this thing is planar. Now it depends, the OH could attack from the bottom, or it could attack from the top. So if this were the case, and don't forget you've got to do your lone pairs on the OH. If it attacks from the top, we get this kind of thing with the OH on top. And if it attacks from the bottom, we get this kind of thing with the OH on the bottom. Oops. Okay, so in this case, you end up with 2 optical isomers. Okay, so if it's SN1, you end up with 2 optical isomers. Now, so the answer is 2 isomers here. And why? Well, because the OH can attack the planar, this thing here. This is a transition state. It can attack from the top or the bottom, from the top or the bottom. All right. So let me post this now. I hope that's okay. All right. Bye-bye.